Hello, and welcome to the Global Precipitation Measurement Missions, or GPM Missions, 10th anniversary. Today is February 27th, 2024, and we celebrate GPM's milestone of being in orbit for 10 years in advancing our knowledge of precipitation and enabling research and societal applications throughout the world. Today, you will hear from GPM experts, providing their perspectives and experiences of the mission, the science, engineering, and applications. So thank you for being here and enjoy the talks. First up, we have a message from Dr. Karen St. Germain, our very own NASA Earth Science Division Director.
Hi, everyone. Thank you for allowing me to join you remotely today. I'm really sorry I could not be there with you in person to celebrate this milestone, but I'm on my way to the nation's largest farm conference. In fact, I'm going to meet with one of GPM's most important constituencies. Farmers, ranchers, crop insurance companies, grain buyers, rail and ocean shipping companies, all of these are stakeholders who are very invested in GPM's mission in one way or another. They are all beneficiaries and users of services and information built on GPM science and observations, critical information to the people who grow our food. Of course, GPM keeps a close eye on rain, snow, droughts, and floods, and you all know that. But the people I'm meeting with this week depend on that kind of actionable information to guide really important decisions about planting, irrigation, market pricing, and harvest. So, in a lot of ways, I see GPM as one of those early mission forerunners of what today we call our Earth Science to Action strategy. From innovation of technology to the satellite missions themselves, to the data, to the scientific understanding and tools that help people and organizations make those science informed decisions, GPM is a model for actionable Earth science. And that's here on the ground today. But from its start 10 years ago, GPM became the model to demonstrate what was then an unprecedented international cooperation. And GPM works because of that model of shared space assets, data sharing, and science collaboration. Your mission has a history of science and observation milestones, from improving our understanding of how raindrop size matters in storms to integrating GPM data into numerical weather prediction and improving weather forecasting. Every mission, every project, and every team in NASA Earth Science is doing something important and doing something big. And GPM has been doing it for a decade. I'm looking forward to many more years of science out of the GPM constellation and the science team. And of course, at this moment, on this day, I'm also missing our dear friend Gail Skowronek-Jackson, and I know many of you are too, but I'm sure that she would be proud. Congratulations to you all on this great day, and thank you for what you do. Go GPM.
Okay. So our first speaker, after we get past headquarters there, is Chris Kummerow. He has a long history of working in the global water and energy cycles. I know him as the guy that drives the passive microwave algorithm for GPM, but he goes way beyond that, has a massive number of journal publications, various aspects, precipitation, the uncertainty in precipitation, and the global water cycle. And I look forward to hearing his history.
Thanks, George.
And the camera is on,
So just forward. Okay, so they asked me to give a history of how GPM got started. And in reminiscing, a little bit, when I started GPM, when all this got started, I was a young kid. Now I was asked to give the Reminiscence talk. So, things have changed. So let me start out by saying that when this was starting, TRIM was preparing for launch. The TRIM project wanted to have a TRIM follow-on. And in fact, two TRIM follow-on proposals had been floated to NASA headquarters. They were not particularly receptive to it. There was not really a program for it. But the hydrology community sort of needed more sampling. All the hydrologists on TRIM kept saying, it's a great mission, but we need 3-hour, 1-hour sampling. And they couldn't get that through TRIM. And then also the international community seemed really eager to participate in this. So the sort of beginning, let's say 1998, I wanted to sort of mention a few people. So Bob Adler was my boss, right? And none of it would have happened without him. But it was during an AMS beer break that Eric Wood, hydrologist out of Princeton, who was on the TRIM science team, was standing next to me saying, what do we do to get more sampling? And being a radiometer guy, I said, well, we launch a whole bunch more radiometers. And then we get to 3 hours. And he seemed sort of interested in that. So the next person who was sort of instrumental in this GPM concept was Dan Golden, who was the NASA administrator at the time, but he didn't actually know me. The reason he's there is because there are a lot of space agency people would go to headquarters and talk about collaboration. And if anybody ever mentioned Precip, they got sent to me. And so I got to meet a lot of people who were space agency representatives who wanted to participate in space programs. And whenever I mentioned, well, you can build small radiometers and add to sampling, they seemed genuinely interested. So that was sort of there. So I sort of started formulating this idea, maybe we can launch a whole bunch of these small radiometers with a radar radiometer, and that would be the TRIM follow-on. But before I said that, I went to Eric Stalker, who's at the time I could go to whenever I had weird ideas, he would sort of straighten me out. So I went to him and he didn't straighten me out. He said, yeah, that might be doable. So off I went to, first Bob. Bob thought it was a good idea. And then I marched to our lab chief, who was Franco Naudi, to see if he thought it was a good idea. And Franco Naudi thought it was a good enough idea where he immediately called his counterpart in code 700 and said they had an idea and, could they assign an engineer to it? Well, that was Steve Neeck. At the time, it was the team of 2. And so I told Steve Neeck my idea of, having a radar radiometer and then building a whole bunch of small radiometers, and launching those. And Steve Neeck immediately said to me, that won't fly. You have to be more creative on the radiometer side, right? My idea was simply to build 8, GMIs. And he sort of straightened me out and said, if you just do that, that's, will not get anybody excited in engineering. And he was so right about that. And I think without that suggestion, we would have never made it through the process. So we enlisted Chris Ruff, who at the time, I never changed that. At the time was actually still Penn State, but I think before we wrote the proposal, actually was changing to University of Michigan. And Chris Ruff had an idea of a synthetic aperture radiometer that we could build for really cheap. So the low frequency channels would be synthetic aperture and the high frequency channels would be normal. And so this was sort of a new novel concept, engineeringly interesting. The cost could be driven way down. And so we sort of put all of that together and into an RFI. And at the time, the Easton Workshop, which was in 1998, is like the precursor to what is now a decadal survey, okay? Where everybody got to present their ideas, and then the people behind the curtain decided what was most important to them. At the time, it was mostly, program managers. But the fortunate thing was that Eric Wood, who was a hydrologist out of Princeton, and who really liked this idea of 3-hour sampling, was also detailed to NASA headquarters in the hydrology program. So he was actually behind the curtain. But we don't know that. So anyway, this is June 8th, 1998 was the proposal, the response to the request for information for the Easton Workshop. This is a paper, so it had a number of co-Is from Goddard, as well as all the other NASA centers, as well as all the internationals, the things we were looking for to build that. So it was sort of fairly politically motivated and represent everyone and make it hard to turn down. So that went in. Basically, the proposal itself, real quickly, 20 years. It had a primary satellite, 65-degree inclination, sort of at the altitude of today. We were calling them drones at the time, the little radiometers, 55-degree inclination. And then the primary spacecraft was sort of like the core today. And the drones were real aperture and synthetic aperture, 26 kilos for the instrument and the bus, the whole thing. I think what we would call a CubeSat today, And we were going to write an IIP, an instrument incubator program, to demonstrate that we could launch the whole thing for 30 million for one bird. The spacecraft and the launch vehicles were all sort of from the catalog and were supposed to be cheap. And so we submitted that in June. In July, the Easton Workshop report came out. Okay, so it was really quick turnaround. So this is, the Easton Workshop was technically the science-based priorities for post-2002, so post-EOS era. And the hydrology and mesoscale weather panel that, had people behind the curtain, their top priority out of this Easton Workshop was global precipitation. And if you sort of look at the text, precipitation is intimately linked to small-scale weather. So you need high space time variability, blah, blah, blah. And basically they sort of summarized the mission that they wanted to be, 10 kilometers spatial resolution, 3 hours. They cut the 20 years to 5, okay? But we're gonna go to 20 anyway. So this is just a midterm review. And then space configuration basically had a mothership in 65-degree inclination and 4 to 8 drones in 55 degree. So they basically took more or less the RFI that we had submitted and said, this is what we need. The new technology was a radar and passive microwave, for the thin array, and the drone required radiometers, required innovation. But I can tell you from the Easton Workshop, the big thing that came out is nobody believed that we could do this for $400 million. And the new technology, the innovation in the radiometers is what sort of allowed us to argue for, but yes, we can. So this was the poster, this was sort of once it was approved. This was the image, and this is still sometimes the image I use for GPM constellation. And then George or Scott remind me that's the wrong image. But this was the original image. Okay? And so by I think late 1999, we had the full formulated mission that had a core satellite, more or less what it is today. The constellation satellites were still, up to 8 launched for this purpose. It only when budget cuts came along that we sort of slowly move away from 8 to ultimately none launched specifically for the program, but using existing assets. And then at the time, I was still fairly naive, right? The program sort of sailed through NASA headquarters. In fact, our detractors always said, it's never been reviewed, it's never been approved. It just sort of failed. So I want to sort of, in retrospect, I thought things just sailed at the time. In retrospect, I want to give thanks to Ramesh because I think he's the one who made it sail through NASA headquarters, right? You always need a champion on the inside, and it just kind of always went particularly smooth. So my time is nearly up. I just want to sort of summarize the trim era is where we demonstrated that the bottom image, which is the radiometer with a radar swath in the middle, the radiometers could do fairly well on their own as long as they had a good radar to calibrate with. And so the top is the radiometer only, the bottom is sort of the blended radar radiometer. So that was sort of what trim showed. In GPM, we sort of demonstrated, and this is now GPM radiometer only, and the ground-based radar on the right. that not only could we go to higher latitude, we could get snow if it was heavy enough. We could do reasonably well compared to radars, still from the space, from the core spacecraft. But I figured George wouldn't kick me off the stage if I showed this, because this was GPM, right? This was actually GPM. The previous slide was the trim follow-on. This was what we worked for to do. And I'm just gonna say it didn't take any effort at all. You see it's done already, but it obviously takes a huge amount of effort to do this. But every time I see this image, this is what GPM was. And 10 years into it, we're here. In another 10 years, we'll be even better. And I'll stop here. Thank you.
There's too many words about me. I have 3 job descriptions besides being project scientist. I'm also the lab chief for 612, and I'm the lead for the multi-satellite algorithm team. I came here in '88 temporarily, and I'm still here. And I will just point out that there's some nice awards here, but that's because I've had a really great chance to do amazing work here. So I want to talk about GPM accomplishments from the NASA side. And then after this, Yukari Takayabu will be speaking from the Japanese side by recorded message. So this is, whoops, you got to show the beginning slide. This is just like, killed it. So there's 2 parts, as Chris has nicely summarized, to GPM. The first is the core observatory. Excuse me. Everyone, including me, calls this GPM, but it's really the GPM core observatory satellite. It was built here at Goddard in the big clean room at the top of the hill, and it was launched in 2014 from Japan on an H-2A rocket. It's pretty spectacular, and I got to admit, that was sort of the 5 minutes of terror until that thing hit orbit. The orbit is inclined at 65 degrees, which means that it looks at all the times of day over an 83-day precession period. There's 2 sensors. There's the GMI, which is gives you a 2-dimensional picture, sort of integrated because it's passive, it's built in the US by Ball Aerospace. And then there's the dual frequency precipitation radar, which has a 3-dimensional data set, which is on a narrower swath and was built in Japan. So it's like, what do you say? So GMI, which is sort of the US side sensor, is the best calibrated passive microwave sensor in orbit, and in fact is used by lots of folks as sort of the standard, and those data are considered valuable for things like tracking hurricanes. The Hurricane Center doesn't just look at things like precipitation, they just as soon look at the radiances and see what the structure of the storm really looks like in different frequencies. On the right-hand side, I've put up an image of the sensor being tested for electromagnetic interference, and gives you a sense of the size of this thing. That reflector is around 2 meters in diameter. So it takes a lot of people to make this, and Art is here in the audience. He was a project manager who led the construction and testing. This was a sort of long process and included things like, we have a centrifuge also up at the top of the hill. So when you get done building it, you mount the satellite on the centrifuge and you spin it around and hope that nothing falls off. Another important job is the lower right-hand picture of shepherding dignitaries around. That's the center director behind the there we go. Then center director Chris Scalise. Back to the camera is Senator Mikulski, and over her head is then Administrator Bolden, looking in the clean room, as most of us did at some point during the construction. This is the construction. Once again, notice the size compared to the people that are working on it. This thing's like a bus. circular boxes of the radar. They put it on a seat and it was mated with a rocket.
SRBへ転化、リフト。SRB 미션을日米共同開発の全球降水観測、GPM計画主衛星と。
I always watch every time just to make sure it really did take off that time too. So it was nighttime. It was early morning of the 28th in Japan. It was the 27th here during the daylight hours. Okay, so the second part of the GPM mission is the constellation, which Chris has done a really great job of showing what the evolution was. We aren't where we started. So the mission goals, as he sort of alluded, it improve the knowledge of the water cycle variability, and then I'll use that information to improve predictions of floods and landslides and freshwater resources. And so the GMI only gives you one snapshot a day. The DPR is worse. It's a narrower swath. You get a snapshot every 3 days. People sometimes get excited when they hear radar in space and they think, you know, your local 88D. No. So we worked with other agencies. Bob Adler and I had actually prototyped this in TRIM, and it was experimental. So we experimentally used other satellites. And when we got to GPM, it was an official part of the mission. So this is just a visualization of what happens if you only have one satellite. Oh, here it comes again. And so we ask the other agencies to send data. Their satellites are doing their own mission, but they contribute data. So if you speed it up here, it's still sort of jerky because it's only like once in 3 hours in 90% of the time that you get data. So the special sauce at the end is you do something to make it smoother so you can get more frequent data. Because what we learned from our competitors at NOAA with CMORPH is that if you have more estimates in time, you get a better long-term average, because otherwise you just get these little snapshots which have space between them. So what do we do with this stuff? Here's an example of a flash flood that was in Washington, D.C. in July of 2019. The background is iMerge, the multi-satellite product, and there happened to be an overpass right at the time of some of the maximum events. And so we're going to stop iMerge and then put an overlay of the core observatory information, and that sort of three-dimensional stuff is from the radar. And so, you know, this gives you some sense of what the structure of the storm looks like if you happen to go over it. Notice in this case that the heaviest rains are at the bottom of the column. The dark purples are at the bottom. What that means is, as the precipitation is falling, it's actually increasing. In some sense, I think there's warm rain process going on in this case. Meanwhile, at the top, it's the blues, that's snow. And so even for a really heavy rainstorm, conventionally, you have snow at the top of the cloud. In fact, over land, we have trouble if there isn't snow at the top of the cloud, because that's what the sensor sees the best. Here's another example of what we can do with these multi-satellite data. This is Tropical Cyclone Freddy, which turned into the longest lived tropical cyclone in history. And in the blues, we have the rates, and in the purples and greens, we have accumulation. So let's fire this baby off. It started between Indonesia and Australia and went trucking across the vast expanse of the Indian Ocean. This is one of the strong advantages that global precipitation from satellite gives you. You can tell what's going out in the middle. There's no other data. There aren't even ships out there in many cases to tell you that they've gotten hit. So Freddy got pretty strong up to a category 5, crashed into Madagascar, damage, Mozambique, damage. Then it wandered around Mozambique. It wasn't the longest lived at this point, but the remnant low wandered back over the Mozambique channel and re-strengthened, made it almost back to Mozambique, went through a couple of cycles and hit Mozambique in a different place, more death and destruction. But the point is that before it hits, the forecasters can see what's coming. It's not just a cloud picture, it's actually the precipitation structure that helps inform the structure of the storm. So it takes a village to build a satellite data set. Here's the science team meeting picture from last summer. Lots of folks, if you squint hard enough, for those of you on the team, you can see yourself. But there's other folks who are involved too, and I certainly want to recognize them. So first of all, there's the Mission Operations Center, which manages the core observatory. Until I became project scientist, I really didn't understand what these guys do, but there's a whole group of people here at Goddard who come to work every day and say, how can I make this satellite work better? The recent boost of altitude to recover some of the orbit time that we lost because of the solar cycle. I was just really impressed at how smoothly things went because these guys really know what they're doing. Then the science teams, both on the US and Japanese side, lead science analysis and algorithm development. I think I missed saying this is a joint US-Japan mission. This is a joint US-Japan mission. Once the data come in, PPS manages the input data, it computes the products, and then it distributes products. This is I feel blessed because some of my colleagues who have other satellite missions don't really have the competence that we see at PPS. It's just amazing. There's also the JESDISC, which does long-term archive, but because they see themselves as an active archive, they also distribute products now, as well as providing some interactive analysis tools. Giovanni is the one that most people are familiar with. Then finally, there's the ground validation part of the project, which Dave Wolf leads. And this is the repository for verifying algorithms and products and really making sure that we are doing what we think we're doing. Okay, well, of course, no such talk would be complete without talking about the project scientists. I actually had to do a little research. It was a little bit vague exactly what this is. I think I've got this right now. Eric Smith was the first formal project scientist. Chris was a study scientist, but not the project scientist early on. Then Arthur Howe, Gail Stefanik-Jackson, Scott Braun, who will talk, and then myself. I think this is the appropriate point at which to say we stop and recognize that Arthur and Gail are no longer with us, which is really too bad. And it also occurred to me that we should mention Joanne Simpson, who is also no longer with us, but was a fierce advocate for this kind of global precipitation work. So thinking about the ground validation part, there have been a whole series of field campaigns, and no, I'm not going to read the entire list, but I did go through and try to assemble lists of field campaigns. These are really important because the reason we do these global precipitation projects is you don't know the answer every place. If we did, we wouldn't need the satellites, but we don't, and so we do. So we go off to places like the Olympic Mountains, the third one down on the right, where there's really interesting orographic enhancement going on that we don't really understand very well. And people, haul equipment up the mountain slopes on burros, and then we get really great data sets that, in conjunction with aircraft, that allow us to get a better sense of what's going on. So there have been a whole series of these. The most recent has been our interaction with the IMPACTS program, which has been on the Eastern Seaboard. There was an interruption because of the pandemic. The 2020, you will see pictures in the conference room of folks bringing back equipment the day before we shut down. So what else do? We send out data. And so these are statistics, which are a combination of JESDISC and PPS. On the left-hand side is the number of monthly unique users. Can't combine those because you can, in principle, some users at JESDISC might also use either PPS production or near real time. But just JESDISC by itself is, we're past 1,200 users, not necessarily the same users, but 1,200 users each month. On the right-hand side is the volume, which you can add together. we're up around 250 terabytes a month. In earth science, that's a big number. In terms of numbers of files, those are in millions, and so the number of millions of files is in excess of 20 a month. Another thing that we do, which has been mentioned, is applications. Yeah, we're going to hear about this, but just to say, this is really a key part of GPM. And if I may say so, it colors the discussion a little bit as to what comes next, because we have hundreds of users who are actively using our data and probably think it's going to continue. So in closing, the core observatory is working well. There are some issues with reaction wheels, but mission operations is on top of that. The JAXA NASA partnership is working well. We have contributed significantly to the precipitation community, and we still have more time that we can do that. And finally, I would like to say I look forward to seeing how TRIM and GPM will continue into the future, advancing precipitation science. So, thank you. Okay, so I get to introduce the JAXA GPM project scientist, Yukari Takayabu. She is a professor at the University of Tokyo, and she is a large-scale atmospheric circulation, convective cloud, precipitation, sort of combination. And she emphasizes the statistical use of remote sensing data. She says that she has very much appreciated TRIM and GPM products since the very beginning of TRIM observations.
Hello, I'm Yukari Takayabu, JAXA GPM project scientist from the University of Tokyo. Thank you for giving me this opportunity to talk in this happy occasion. First of all, happy 10th birthday, GPM Core Observatory. For this talk, I was asked to discover the reasons for this successful mission from the JAXA's perspective. From the beginning of the GPM project, we had tight connections as a TRIM heritage. These photos are from November 2012 at the award ceremony held in Tokyo. The certificates of appreciation from Dr. Freilich and Dr. Homma were given to 8 Japanese and US scientists. Please find their faces. Drs. Kenichi Okamoto, Kenji Nakamura, Tasuku Tanaka, Tetsuo Nakazawa, Ramesh Kakar, Chris Kummerow, Bob Adler, and Eric Stocker. The GPM Core Observatory was originally scheduled to be launched in 2007. The team overcame numerous administrative crises, continued development of the DPR by patiently slowing down its speed, said Kojima-san, JAXA's GPM project manager at that time. The launch was extended twice and finally decided to occur before March 2014. Over the mountains, DPR was finally handed from JAXA to NASA in March 2012 at NASA GSFC. GPM grant system is an essential part for data users. It is surprising to find so many steps before we can use the data. The ground system team also keeps good connections from the trim era. The top photo is taken in 2005. The middle is in 2016, and the bottom is from 2023. We can see how people grew up to become wonderful leaders. On 28th February 2014, we were there at the GPM launch in Tanegashima. In the top right photo are Rico, Gail, and myself. It was a wonderful launch. I can never forget. These are scenes of external calibrations at JAXA Tsukuba Center. It is amazing that these receivers really capture the DPR signals flying over at the speed of 7 km per second. With extraordinary efforts by the team, external calibrations went successfully. Targets of the DPR algorithm developments were: first, keep similarity between the PR algorithm and the KUPR algorithm. Second, secure consistency between KUPR algorithm and KAPR algorithm. Third, make sure to show an advantage of dual frequency algorithm against the single frequency algorithm. Wow, it's tough. But with wonderful international collaborations, radar team has accomplished this task. Ground validation of DPR were conducted in various sites in Japan. Especially, focuses were placed on the Ka radar attenuation profiles through melting layers. With ground-based dual Ka radar system developed by JAXA, led by Kenji Nakamura. A few examples of DPR applications with KUPR heavy precipitation characteristics were clarified. This is an example of July 2018 torrential rainfall event in Japan, observed by GPM DPR. Despite the record-breaking rainfall amount in this event, rainfall height over 10 kilometers is scarcely observed. This is a typical heavy precipitation in a very moist season without significant cape instability. Another is the global three-dimensional latent heating estimate from KUPR observation. Convective heating plays an essential part in the atmospheric energy balance. It is also an important driving source of the atmospheric general circulation. So, estimates of convective heating from the satellite measurements are very important for weather and climate. One good example of the dual frequency data use is the flag heavy ice precipitation by Iguchi et al. They utilized Ku and Ka differences in measured apparent radar reflectivity and enabled the estimation of heavy ice precipitation. And of course, efforts are integrated to produce high spatial temporal resolution precipitation data, GSMAP. There are various versions of data, including the nowcasts and precipitation forecasts. JAXA also collaborate with various model communities to utilize satellite data in their models to enhance future predictions and contribute to science and society. Among them, GSMAP collaborates with atmospheric models and land river models. Every year, we get together to celebrate the GPM birthday. This is the GPM third birthday party in 2017. And this is the fifth in 2019. And for the sixth in 2020. Each year, GPM birthday cakes are produced by Tomohiko Higashiwa Toko. We enjoy them very much. Congratulations! On July 11th last year, Dr. Riko Oki received Exceptional Public Service Medal of the NASA Administrators Agency Honor Awards. The most recent activity was the successful orbit boost in November last year to elongate the lifetime of the GPM core observatory against the high solar activity. Now we can expect some overlapped measurements between GPM DPR and PMM KU DPR. These collaborative experiences will certainly help the next mission. Conclusions. Our strength lies in our international and interdisciplinary ties. Thank you very much.
Okay. Scott Braun is up next. He is a fellow research meteorologist here at Goddard, and he is a project scientist for AOS, as well as tropics. He was my predecessor here in GPM, but in addition, way back with TRIM. Whoa. And so he comes from a atmospheric science background through University of Washington, AMS fellow, and he focuses on sort of weather, convective systems, tropical cyclones, and winter storms. Scott.
All right, thanks, George. And before I move on, just one of the things that wasn't on Yukari's little bio slide was that she also recently won the Joanne Simpson Award, which is a big award from the AMS now. I think we've have had 3 of them so far, and I think it was very fitting for Yukari to get that. I kind of view her as the Joanne Simpson of Japan, basically. So I was really happy to see her get it. All right. So I'm here to basically talk about the future and what follows GPM, and that's the Atmosphere Observing System, which came out of the 2017 Earth Science Decadal Survey, which had recommended a number of targeted observables, or the major ones were the designated observables, and it's addressing both aerosols and clouds, convection, and precipitation. It's been the result of a fairly extensive study both the science and the best way to address that. And then over the last couple of years, how we try to implement that science. So what is AOS? And I'm sorry that the titles are being kind of cut off here by the team's information at the top, but it's a mission that's basically trying to get transformative observations of atmospheric particles from aerosols to cloud droplets and precipitation particles, and how that impacts weather, air quality, and climate. And so it's a fairly, I guess, aggressive approach to getting these, and the rationale is that in trying to look at the coupling of aerosols, clouds, and precipitations, you can't do it with a single sensor. It really takes a multi-sensor approach. Some of the science themes for AOS are climate sensitivity and feedback, convective storm processes, particularly tying the microphysics to the dynamics of convective storms, and then aerosol processes and distributions. We're looking at aerosols and their interactions with clouds and how that is a key driver of uncertainty and climate. Aerosol impacts, particularly from an applications perspective in terms of air quality, human health, aviation in terms of volcanic ash and how that can disrupt aviation. In fact, George and I, when we flew to Japan last fall, got to get to Japan by flying just north of Hawaii because you couldn't fly over the Northern Pacific due to volcanic activity. So it can, and they had canceled a large number of flights. So it can be very impactful. And then in terms of convective storms, we've seen, if you look at the NOAA data for billion-dollar events, there's been about a 7-fold increase in billion-dollar disasters over the last 40 years. Now, that's not all due to the weather. That a lot of that is increasing development in coastal areas and so on. But there's no doubt that storms play a role in that. With climate change, we expect greater numbers of storms and more intense storms. And a lot of that increase was tied to severe convective storms and tropical cyclones. In fact, that was the majority of it. So let's start with aerosols here. This is a nice simulation from the GMAO showing the evolution of different aerosol layers. You can see the Saharan dust coming off of Africa in the brown and white. You get these major eruptions of dust that over the Sahara that then move all the way across the Atlantic. And you'll see in time here, tropical cyclones develop. They develop right on the southern boundary and sometimes the western boundary of these dust outbreaks. Another thing you'll notice with these storms is the white to blue colors. That's sea salt that is basically emitted into the atmosphere through evaporation at the ocean surface due to the strong winds at the surface, particularly in these storms. And then we have smoke, in this case generated in the Pacific Northwest, that gets carried well downstream. And of course, last summer we experienced that directly here from the Canadian wildfires and the type of pollution it generated for us. So part of AOS is looking at these types of particles, their properties, their evolution from emission through transport and eventual removal. The cloud precipitation and convection aspect of AOS is really focusing on the broad distribution of clouds, high and low clouds, convective storms. And if you look in this animation, you also see in blue the aerosols from biomass burning, brown from Saharan dust, and there's some other areas from wildfires. And the reason I like to show this animation is because these particles are occurring together. Those aerosol particles provide the seedlings for the cloud droplets. The number and size of those particles determines the distribution of cloud droplets, how effectively precipitation is formed, and how quickly aerosols are removed from the atmosphere. So these coupled processes are critically important. Their interactions also are very important for projections of climate. The biggest uncertainty in the radiative forcing of the Earth and climate models is aerosols and their interactions with clouds. And this mission is really intended to try to look at these interactive processes in a single mission. So our approach here was to use multiple sensors, recognizing that each has their strengths and weaknesses. They see clouds, aerosols, and precipitation in their own ways, and that by themselves, they're not sufficient. It's kind of like the blind men feeling the elephant, and each coming up with a different conclusion of what it is they're feeling. And it's only through the bigger picture that you're able to do this. I show this animation of these clouds because, you know, if you're trying to get measurements and you have a constellation of satellites that are sort of disconnected, you're going to be observing things at different locations at different times. But if you're trying to understand these processes, you got very small scale clouds on the order of a kilometer or so, evolving up into larger cloud systems, and they're evolving very rapidly. This is 1 minute imagery. So ideally, you want to get coincident in time and space measurements of the aerosol cloud and precipitation properties, and that is what AOS has been trying to do. So this is the AOS architecture as it is right now. I kind of say it that way because, as you know, there are budget pressures at the moment. It was interesting getting Chris's perspective on the evolution of GPM, going from a large number of drone satellites to eventually what we ended up with. AOS, I hope, doesn't experience that much change, but we know probably some changes coming. And we're looking at ways to most efficiently implement as much of this as possible. And we're awaiting the outcome of the budget to kind of chart the path forward here. But one of the things that we tried to do to make this happen is to take advantage of some key international partnerships. So during the study, we were looking to deliver what the decadal survey identified as some of the primary instrument technologies: Doppler radar, passive microwave radiometers, backscatter LiDAR, and a multi-angle polarimeter. We had the Canadian Space Agency come to us with a far infrared imaging radiometer that can provide imaging of thin ice clouds, gives you the optical depth, particle size, and outgoing long wave radiation. And then they had another system they call HawkSat, which are limb viewing aerosol and moisture profiles so that you can see the interaction of clouds with aerosols and moisture in the upper troposphere and lower stratosphere. JAXA came to us with their PMM radar. It's basically a KU radar, much like on TRIM, but has Doppler capability at nadir, using two antennas to use what's called a displaced phase center antenna approach that effectively removes the spacecraft motion from your Doppler estimates to give you the most accurate Doppler wind fields that you can get. And the goal here is to get good measurements of the vertical velocity in convective storms, particularly larger convective systems. And CNES in France came to us with a concept for tandem microwave radiometers. So it's high frequency radiometers from 89 to 325 gigahertz that will provide information on ice water path. And we can use it for precipitation measurements, although it's not as good as when you have the low frequency channels. But their idea is that by having two radiometers, identical radiometers, separated by about 2 minutes, you can look at the rate of change of those cloud properties. They've demonstrated that at least for certain stages of the evolution of convective storms, you can infer the vertical mass flux within those convective storms. And that will pair very nicely with the Doppler radar from JAXA. So overall, we got 4 satellites, 11 instruments, and 3 international partners. This year or last year, we started looking at another international partner, the Italian Space Agency, to provide a backscatter LiDAR in the Polar Observatory that would do better than what we thought we can get from industry. And basically the AOS sky measurements, which are in the Polar Observatory, are really intended at getting at these coupled aerosol cloud and precipitation properties. And the inclined orbit is focused more on the convective properties, relationship to high clouds, and aerosols in the environment of convection. So looking into the future of precipitation analyses, I will say that AOS, due to budgetary constraints, wasn't able to really build into the budget continuation of level 3 products. And we've been talking with headquarters about how we can build continuity in those measurements, but we are doing everything we can to at least enable those measurements by having the PMM radar. So AOS will provide the KU band radar and 2 microwave radiometers, really 3, but 2 are so close together that from a precipitation sampling perspective, they're giving you kind of the same answer. We do envision that Tomorrow.io will have their constellation active during this time. My understanding is 12 Ka band radars and 18 tropics-like radiometers. So, when you think of an IMERS-like product, the hope is that we start replacing some of the IR-based estimates with more active measurements and passive measurements. So that should advance precipitation capabilities. And then there are other sensors from operational centers. I think the number of imagers are going down, except for some of these higher frequency ones. So that will present some challenges. Right now, we do the merger in the way of iMerge, in which you take the information that's there and you fill gaps through either the morphing technique or the filling with IR estimates. I think in the future, and this kind of goes back to what Arthur Howe was envisioning for GPM, was what we call level 4 products, where you integrate the observations into a global climate model to generate precipitation analyses. Arthur always envisioned that, but we never quite got there. But I think when we look at the sort of modeling improvements that are likely over this decade, we're getting global models that are gradually pushing down to convective permitting resolution, potentially even cloud resolving resolution by the end of the decade. We're seeing advances in forward models, and there's a lot of people here working on improving the properties of the ice particles and how that leads to scattering in these microwave channels, and the ability to assimilate that through all sky assimilation into the forecast models. I think that also will benefit this type of approach as well. I haven't addressed it here, but I'm almost certain machine learning is going to play a significant role. We've seen the advances, for example, that Google is making with machine learning and such. So it's almost inevitable that that's going to happen. We don't know at what point the precipitation that's integrated into the model is going to surpass what iMerge is able to do now. I suspect that we'll see some point this decade that we may get there. And even if it gets comparable to it, maybe we can get to, as George called it, a level 3.5 product, where the precipitation analyses that come from the models can be used to fill in those gaps where we don't have the microwave data. So replacing the not nearly as accurate IR estimates and thereby improve precipitation estimates in that way. And so just the final slide here, just illustrating some of the differences here between GPM and AOS. GPM was really focused on precipitation mapping with a heavy emphasis on applications. AOS is focused on applications as well, but it was a bit of a too heavy of a burden for us to carry the precipitation mapping in addition to all the other things. I was going to say at the beginning, the study for AOS involved people from CloudSat, Calypso, and PMM, those communities. It was a lot of different personalities with their own interests, and we had to try to balance those in a way, and we thought it would be rather difficult to do. And luckily, the group worked pretty well together. We're certainly facing some challenges, both with costs within the mission, but also with just the current budget situation. The AOS mission, it gets broader than precipitation by itself, obviously, by folding in aerosols and clouds. But we're hoping that this will lead to new science that can be done over the next decade, but still allow continuity for these other communities. So I'll stop there.
No GPM celebration week could be complete without Ramesh. He was a program manager at headquarters for essentially the entire development of GPM. And he has just done an amazing job at sort of herding the cats, keeping things focused and moving forward, sometimes in spite of, and sometimes with the cooperation of other people at headquarters. So as I said, he started with doing this with TRIM and then did it again with GPM. At his retirement, he was a program scientist for several satellite missions, not just GPM. Once again, I'm sure, as I would say, that if you have multiple job descriptions, they always peak at the same time. And I'm really pleased to have him have a chance to say some words. Ramesh.
Okay, so how do I forward it?
Oh yeah, wait a second. There you go. And now you can.
All right, I'm so happy to be invited here today. Let's see what I can say here. I want to talk about the year 2005 in the context of TRIM and GPM. Even though GPM is the star of the show today, I want to mention TRIM also and recognize NASA higher ups had canceled a new start for GPM in the 2006 budget, believe it or not. I also want to highlight the support provided by Dr. Mary Cleave. So on August 22, 2001, NASA completed a set of maneuvers to boost TRIM orbit from 350 to 400 kilometers to prolong the useful life. However, TRIM was expected to hit the minimum fuel threshold for controlled re-entry in August 2005, and the ESD, our science division higher-ups, were leaning towards deorbiting it. There was a very strong sentiment at NASA headquarters that we want to deorbit TRIM. I don't have a pointer, but pay attention to the horizontal axis there. TRIM was originally at 350 kilometers, and we used some onboard fuel in 2001 to raise the orbit to 402. If we had not boosted it, it would have gone into the ocean in the year 2003. So, but by the time we got to about August 2005, the remaining fuel was just sufficient for a controlled re-entry, and the higher ups at NASA decided that we are going to use that for a controlled re-entry. So astronaut Mary Cleave came in as associate administrator for Earth Science in September 2005. She worked with the new NASA administrator, Mike Griffin, to make the ultimate decision to eliminate controlled re-entry and keep TRIM going. The outgoing associate administrator for Earth Science saw the writing on the wall and removed JPM New Start from the NASA budget for 2006, arguing that if TRIM continues, we don't need GPM. So, GPM almost didn't happen. However, August 29, 2005, Hurricane Katrina hit the mainland. Soon thereafter, President Bush's science advisors got concerned that after TRIM goes away, there is no similar satellite to monitor future hurricanes. So soon, the President's Office of Management and Budget contacted Mary Cleave, our associate administrator, and told her that NASA cannot cancel GPM. So long story short, on Christmas Day 2005, I was answering nearly 20 OMB questions, and I could not get help from any of you because these questions were related to the President's 2006 budget, and this was embargoed information at that time. So, and ultimately, OMB provided funds for GPM and a low inclination orbiter over and above the NASA 2006 budget. So this was, Katrina helped us, and this is, otherwise there would have been no GPM. If there was no Katrina, there would have been no GPM, believe it or not. So Dr. Mary Cleave passed away in November 2023. We are very grateful for what she did for TRIM and GPM community, and we want Mary Cleave to rest in peace. That's my presentation.
Thank you, Ramesh. I think there are other stories that can be told about the salvation of Trim, but enough people have to pass from the scene and maybe statutes limitations run out, and then we can tell the rest of the story. Okay, next up is Steve Neeck. He worked for at headquarters, and in particular, before that, he was working at Goddard and has had a career in satellites. I've known him a long time. Once he went to headquarters and was instrumental in several international organizations I was part of. I appreciated his leadership in those as well. Steve has another perspective to bring to GPM.
Thank you, George. Yeah, thank you, George. How do I move on? Just okay. First of all, I'd like to say I'm very pleased to be here today and grateful to be here on this day of celebration and also remembrance. You've seen at least these charts in a different context. This shows the system architectural evolution through 14 years of GPM. Chris Kummerow particularly addressed the right-hand side of the reference concept, and on the left-hand side, I'm sorry, the left-hand side is the reference concept, the right-hand side is the at-launch concept. And when you look at it overall, the architecture is very stable over the 14 years from pre-phase A, advanced studies, to the at-launch state. The segment elements, both space and ground segment elements, are also very similar. But there were a number of changes in the details, changes driven by budgetary pressures, changes driven by technical considerations, both in the core observatory and in the constellation spacecraft. As you can see, on the bottom, the constellation spacecraft evolved, as Chris originally indicated, from a NASA-contributed collection of heterogeneous small satellites carrying passive microwave radiometers to a big red X, which really reflected the removal of the NASA components and the addition of international and other, like NOAA, operational systems to provide the international virtual constellation that provides the passive microwave radiometer aside from the GMI and the core observatory today. The core observatory also evolved. It evolved in its implementation approach of the spacecraft bus from a rapid spacecraft development catalog approach, as Chris referenced, to a in-house approach with a hybrid scheme in between, and also later on in the implementation phase, GPM core observatory, the end of mission approach was changed to controlled reentry, as you heard reference to also. International partnerships, as you've also heard, have played a big role in GPM, not only with the critical partnership with Japan on the core observatory, but also in terms of the constellation satellites. And here on the lower left side are a collection of partners we interacted with over the years, some who actually ended up being part of GPM at launch, which is reflected on the right side logos, agency logos, and some that did not. Some that had substantial contributions hardware-wise that we interacted with them on, but that just didn't work out. There were 8 international planning workshops from 2000 to 2009 in which we explored and discussed partnerships, and they're very valuable in maturing them to the point of where they were realized. I'll move on to also some perhaps lesser known facts that may be of interest. GPM was a subject of a major Indian Bollywood film in 2004. Are you aware of that? And it starred at the time, one of the two top male actors in India, Shah Rukh Khan, as the project manager. On the upper right, I think with a bit of a haircut and some makeup, Art could serve as a reasonable double. But the formulation manager at the time, John Durning, wore a ponytail and he never would have passed. The chap on the left with the old school tie is supposed to reflect an amalgamation of Ramesh and myself. And I tried to get my AI app to merge our portraits to see if there was any match, and it just choked and refused to do so. Plus the British accent was not very convincing either for the two of us. But it was shot. The script was carefully reviewed at NASA headquarters. This was, as I said, in 2004 in a very formative stage of GPM. And the film was shot here at Goddard. You can probably maybe I think that's building 28 inside in the atrium where they used to have this big globe. I don't know if it's still there or not. And it was also shot at Kennedy Space Center, launching on a shuttle for some reason. Another fact of GPM, and certainly our esteemed project management colleagues somewhere in back. Art, where are you? There you are. Okay. Is Candace here? No, she couldn't make it. Okay. Candace was Art's deputy. But in any event, there was a major earthquake in Japan in 2011, which I'm sure you're very well, a very tragic and tsunami. And it impacted, it was right at the time of the completion of testing of the DPR at Tsukuba Space Center, northeast Tokyo. Thankfully, the flight hardware was not damaged, but it caused a really significant delay in the testing, completion, and also shipment to Goddard for integration with the core spacecraft bus. But the Japanese worked through that. And ultimately, in March of the following year, it was about over a 6-month delay. It was delivered, and on the lower right, you can see the acceptance handover ceremony with all the smiling faces there here at Goddard. On the way to Tanegashima, after the completion of spacecraft integration and testing, stormy weather interfered, adverse weather, both on the outbound trip, the C5 Air Force cargo flight to the landing site in Kyushu was delayed. It was diverted to Alaska due to strong headwinds, so the planned aerial refueling would not get it there the whole way. And then once in Alaska at Elmendorf Air Force Base, icing, aside from some other issues, prevented continuation of the flight for a day or two. And then on arrival in looks like sunny weather in Kitakyushu, Japan, the core observatory was transferred to a freighter, a barge, and then sailed down the inland sea to Tanegashima. And on the way, adverse weather interfered and forced the ship into port for a while. But ultimately, it did arrive intact at Tanegashima. They don't have a big airport, so they can't fly direct into it. So everything's barged there. And that was the end of that story. But it did lead to the clear skies, or at least mostly clear skies at launch early on March the 28th, February 28th, Japanese Standard Time. And with that, I'd just like to, as others have, recognize the prominent roles of two very strong and fine project scientists with whom I was able to work, had the pleasure of working with, as have many of you, Arthur and Gail, and of course, to all the others in both the scientific and engineering communities have contributed to the success of GPM, which we celebrate today. So that concludes my talk. Thank you very much.
Thank you. I can honestly say with these last couple of talks, I've learned some things, or I remembered some things. Yeah, that earthquake, I remember, yeah, we're all sitting around going, oh, no, what now? And thankfully we recovered from it. We're not going to go into a series of lightning talks, which is a cue to the folks involved to be lightning-like. But everyone so far has done a really great job of staying on schedule. Thank you. So first up on the lightning talks is click. There we go. You know, in the old days, and my favorite joke is, in the old days, all you had to know was how to change the light bulb in the overhead projector, and you were like the king of audio visuals. Okay, the first lightning speaker will be Bob Adler. He came to NASA Goddard while I was still an undergraduate. He was the head of the mesoscale branch, so one of my predecessors. And he was a TRIM project scientist. And it doesn't say this, but he also was running the multi-satellite experimental algorithm in TRIM, which I was associated with. Since he retired in 2008 from federal service, he went to the University of Maryland, where he's only semi-retired. Okay, Bob.
Thank you, George. I'm going to talk a little bit about GPM and climate, but first, a little look back in time. Before a 10th anniversary of GPM, there was a 10th anniversary of TRIM. And I'm going to raise my TRIM artifact thanks to JAXA, because probably NASA can't put out this kind of stuff. I'm going to raise it. We're going to have some liquid refreshment later, right? To GPM's accomplishment. But things go back even much further, 20, 30, and oh my gosh, even 40 years. Because in 1984, which is 40 years, that's when the TRIM concept was first proposed by Jerry North, Tom Wilhite, and Otto Thiele. And actually in 1984-85, there was Japan Radio Research Lab, that's what it was called back in those days, and Goddard started doing radar flight experiments. I think first in light aircraft and then later I think on P3s. And in 1985, you can see here the cover, there was actually a first TRIM science workshop on the requirements. The report didn't come out actually until 87, but the workshop was in 85. But then things really got going a little bit later. There was another TRIM workshop in, I think, 1986. And I put some of the names up there, and you can see on the Japanese side, Fugono, Matsuno, and Nakazawa, and others, Okamoto. And in the flight experiment activity, Okamoto, Nakamura, and Kozu were involved. And over on the US side, John Thean, of course, Joanne Simpson, Bob Howes, Ed Zipser, Bob Meneghini here is in the audience. He was involved with the Japanese in those radar flight experiments. And Chris Kummerow was also involved, actually, he wasn't there for the workshop, but he was, his name is actually mentioned as contributing to the report I have up there, also Bill Lau. And there were a bunch of the rest of us in the et cetera thing. My point is that this US-Japan thing has been going on successfully for quite a while, and I think it's important to keep it going. We'll go back to GPM and climate here, and George, myself, and other people, including Dave Bolvin and Eric Nelkin here at Goddard, are involved in something for a number of years called the Global Precipitation Climatology Project, in which we put together various satellite data and actually surface gauge data and produce a climatological record. And the most recent version of that, which is the images up there of the version 3.2, of our product has GPM and CloudSat data in it in terms of setting the monthly climatologies that we use in GPM. We still, variations from those climatologies are driven by polar orbit passive microwave, but it certainly is a contribution of GPM to climatology and the long-term data record. And this advancement over the oceans has actually resulted in a higher mean ocean precipitation rate than we had before. And that's actually helped in terms of global water and energy budget type of activities. And you can read about it. There's a recent article in a Journal of Climate. And also in terms of higher resolution type of thing, we also have a daily climate product, which utilizes iMerge over most of the area of the globe to provide some space-time variations. And we're putting out a daily product, and it's driven against that monthly product. So we take out some of the inhomogeneities that you find in the normal iMerge product and produce a climate-ready product that people can use. And we have a record from 2000, which is the beginning of iMerge, up through now 2023. So my point again here is that GPM is really contributing not just to a lot of other studies, but also to improving the global climate record. So I'll just summarize by saying the first two things are related to that climate record. And then at the bottom, the US-Japan partnership of over 40 years has been very successful, and we need to hopefully continue it into AOS if possible. Thanks.
Bob reminds me that if you look at the parentage of iMerge, TMPA before that, it actually goes back to the original GPCP. That was the first thing we proposed for trim. Okay, the next data utilization talk is Chris Kidd. Whoops, click. He's our favorite UK scientist. He's been at Goddard probably longer than he's been in the UK. I don't know. So he's bounced back and forth a few times at University of Birmingham, worked on satellite meteorology and climatology. And since then has been involved with various projects with NOAA, NASA, way back in the WetNet project. For some of you old timers, that was a real watershed, so to speak. And then besides being part of the NASA PMM science team, he's in the precipitation virtual constellation for CEOS, and is a member of the National Academy of Sciences Committee on Radio Frequencies. If someone's trying to steal our frequency bands, Chris hears about it.
Thank you, George. One thing I'll put straight from the beginning, I'm a geographer. And you might think, strange, but I did geography, physics, and math, which I thought was a really odd combination at the time, but in fact, it's incredibly useful because actually putting geography into distributions of precipitation together with the maths and physics associated with it is absolutely perfect. Okay, so one thing I did a couple of weeks ago, and in fact, so sort of George and a few other people, was to do a 10-year composite of the GMI data. And you get beautiful pictures like this because there aren't any clouds. And in fact, when you look at 5-kilometer resolution, you can see incredible detail using the GMI sensor. And that's sort of something that's probably going to become more common in the future with future missions, higher resolutions, and so on. In terms of personal journey, it's sort of interesting to think that 40 years ago, I stood at the threshold of starting my PhD. And not quite 40 years ago, but 3 years later, typical computers in those days, FACS 11750, 2 megabytes of RAM. Your mobile phone has 16,000 times that amount of memory. We still did things though. As George noted, I cut my teeth on the NASA WetNet project. And looking at some of the sort of wording there, you're thinking, wow, you're actually getting scientists together to actually do things collaboratively. It's quite a thing. And there's one of the original slides which I dug out from the WetNet project, primarily sort of centered around the DMSP SSMIS sensors. And there you have a list of contributors to the WetNet project. You'll see the few familiar names, quite a few unfamiliar ones as well, but Bob Adler is in there right at the very top. So some things never change. And the actual sort of NASA WetNet team in 1989. One thing I must say that by the time we sort of transformed into the PMM science team, color got a lot better. So of course, precipitation or not, okay? So we either have too much of it or in many cases, too little of it. The first case was the recent atmospheric rivers in California. This is a current drought situation in eastern Spain and North Africa. And there's been a big campaign which basically says water does not fall from the sky. You have to be careful because that's in Catalan, not in Spanish. If you try doing it in Spanish, it comes up with something like there's no water on my phone. But one of the key things is to remember that water is actually very valuable. We turn the tap on and water comes out and everything, and it's fine. But if you actually work out at, say, $2 a ton, $2 a cubic meter, global rainfall contributes about $258 trillion to the economy. Global GDP is only 104 trillion. Over the US, it's worth about 13 trillion. Compared to GDP of about 23 trillion. So it is actually very, very variable. And of course, it's actually when you actually look at what water, how much water is involved when it just makes some of the basic things. So 24 tons of water is required to make 1 kilogram. You know, it's just mind-boggling when you look at some of those numbers. So of course, why do we need more than just the before, as George alluded to earlier? Well, because of the variability of precipitation over time and space, basically GPM alone cannot measure global rainfall. So we have all of these different partner missions, all of the different flags there. I'm sure I've missed out one or two, but basically we have the US, which includes NASA, NOAA, Department of Defense, Japan, 30 member states of UMETSAT, and India have all been involved with GPM one way or another, either providing satellite data or ground validation stuff. So it is really a truly international effort to measure this global precipitation. And when we look at this timeline, you can see sort of right on the far left-hand side, you've got the number 7 of 1978, which sort of transformed into the SSMI and SSMIS series. We've had a series of sounders, which are shown in the green, and of course, TRIM and GPM. But of course, TRIM and GPM have really been the only precipitation missions. All of the others, we've actually sort of got the data to improve the overall measurements. And in fact, when you look back to the sort of 1985 sort of time frame when we just had simmer, basically, that only came over every other day. They switched it off to save power. So global coverage, you only got once every 6 days, and so it was very difficult to measure global rainfall. As we progress through the years, up to 2015, when GPM was fully operational, we obviously had far better coverage, this sort of 3-hourly data, 90% of the time on a global basis. Into the future, obviously we have the current GPM constellation and hopefully GMI going out to the sort of 2030 timeframe. We also have a whole swathe of baseline missions, which will provide the sort of core measurements. But of course, we also have an increasing use of CubeSats and smallsats from both the major agencies and organizations, but also from commercial providers. then just finishing off a small video on the right hand side. This was Bill Pettersen in the CTX kind of ping weather launching the radius on. The key thing is that GPM provides unique set of pointers. Natural factors contribute to this all, provides a focus natural and also the GPM outreach is actually crucial for using the exploration.
Can I go first? All right. We'll still talking string here. All right, off we go. There we go.
Okay, thank you. Okay, our next speaker is Dr. Courtney Schumacher. She's coming to us remotely and I think live. She's been a professor at Texas A&M since 2003, was involved with PMM, starting with TRIM when she was a graduate student, and she's no longer a graduate student. Now she's a well-respected professor. She's been a member of the Joint Precipitation Science Team, which is the joint US Japan science governance body. Says she's fond of organized convection, but that she has done some really interesting work in what we recognize as, the nasty stuff that we all try to avoid if you're not studying it. So with that, I'm going to see what it takes.
Great. Well, I'm really honored to be speaking today, and I very much wish I could have been there in person. But in lieu of that, I'm going to ask you to take a trip to Oz with me, and we're going to talk about the DPR and atmospheric convective processes along the way. So we've known since well before the launch of TRIM that the tropical convective cloud population has distinct elements, including the shallow convective, deep convective, and anvil or stratiform components. And those are all very dynamically and microphysically unique. And then TRIM, when that was launched, it allowed us to see these populations across the tropics and into the subtropics. It was wonderful. It was a wonderful time to be part of, the mission. But there must have been more, and you think something more we can do than just TRIM and with what we can see with the PR. And of course, you guys guessed it, it was the launch of GPM and the DPR on that satellite. And with that, the DPR expanded our view of these rain types into the mid-latitudes. And we could see that there's this very rich diversity in terms of the latitudinal variations and the geographical locations that have led to a lot of papers in the interim period. Today, because it's a short time and it's just supposed to be a more personal journey, I'm going to be just talking about my own papers, and my own perspective. But I know I have a list of many that I would have wanted to include, and many of you are there in the audience today. And this is a journey for me. This is also 20 years between these two papers that came out. And so, yeah, so what do? You have this, so now we're in Oz. Welcome, everyone. Now everything's, it was on purpose that it went from black and white to color on those two images. And so once once Dorothy got to Oz, she needed, some help along the way. And she met the Tin Man and the Scarecrow and the Lion, and along the way they helped each other, and they made technical improvements and emotional improvements. And in this case, I'm going to say the improvement that was made with the DPR was the enhanced KU band sensitivity. What did it, what new things did the DPR allow us to see? And that is a lot more weaker rain, whether it be shallow convection or on the stratiform rain. So we had a much better view of the climatologies that we were looking at. We also had a much better view of echotops, a much more realistic view of how deep convection could be, or how deep the stratiform clouds could be, or a more accurate estimation of warm cloud processes. And I want to point out that these are CFADs of reflectivity averaged over 2-degree boxes. So they're not exactly what you'd expect from pixel view, but it's sort of what a GCM would have expected. So these are one of the, kind of future uses of this, is to continue looking at how GCMs view the world as as the PR and DPR do. And I did choose the line because I feel like he became more sensitive. That picture was supposed to represent that. Okay, but of course you're like, well, what about Toto? So in this case, Toto, if you could guess, is going to be the addition of the Ka band. So the DPR was dual frequency. It added the second frequency, really allowed us to do more interesting DSD retrievals and representations, better rainfall estimates, and also better classifications of rain types into these shallow and deep convection and stratiform. And we can see that it allowed us, again, to this more accurate and higher fidelity view of latitudinal rain distributions of these types, but also the geographical variability. Again, this very rich view of where convection is more of an active player, for example, where you have more of these magentas and blues. And then as you transition into the extratropic stratiform rain becomes the driver, the convection is in the backseat. And it's really interesting to consider the different kind of dynamics and synoptic settings that play a role in these different types of rain contributions. But of course, this is not always the case in the mid-latitude over land. Things can be much more convective in nature. So convection is not just in the tropics, and DPR is letting us see that. And then this is supposed to represent as the day goes on. Dorothy fell asleep in the poppy field, but in the other beautiful thing about GPM is its inclined orbit, and especially the extended time frame of this 10 years is so important for us to get an accurate diurnal cycle. And when you add that to the PR together, it's just an astounding view of diurnal variability of these different rain types. And so, for example, the shallow or warm top convection, and over the ocean, that's where you get the early morning maximum, where over land you get the kind of more around noon or so. And as that convection deepens, everything gets a little later in the day, both over the ocean and over land. And you continue that evolution, the organized convection I like so much. And then that you can start seeing, again, even later in the day, these are where the really big systems are forming and lasting a long time. And you're starting to get beautiful kind of rainfall patterns, which is indicating propagation. And so I think with that, I just wanted to say that I think the DPR contributions to science and society are both parts of the benefits of the DPR, this higher inclination angle, its greater sensitivity, the added wavelength, the extended record, have made it possible to have these near global observations of convection. And their 3D structure, that's a very unique aspect of the radar. And then this really high fidelity, allowing us to look at the physical mechanisms behind rainfall extremes throughout the diurnal cycle. And then lastly, this is a way to thank the leadership. Again, we've been hearing so much about the leadership throughout the day. Gail's obviously Glinda, but others, we have lots of different Oz's that have been led us so well. And so thank you for that. But also mostly, I would like to thank everyone here for being such wonderful colleagues. It's a community that makes GPM what it is. And thank you for being on the brick road with me on this.
There is currently an assistant professor at University of Michigan, which she joined in 2022. Before that, she was at University of Wisconsin-Madison for more than 15 years. She works one of those really important areas, intersecting science and instrumentation, and she uses whatever she can get her hands on, which I appreciate. She was a recipient of the 2019 NASA Early Career Award, and she's a 2024 Mercator Fellow for the German Arctic Amplification Project. And you're going to tell us what that means.
I'll tell it's a
Claire.
reception. Thank you. Great. Hi, everybody. All right. So today I'm going to talk about cold precipitation, but from the ground validation activities perspective. And this is really contributions from tons of people, but the stuff I have in the slides here is from these folks, and has really been wonderful taking a trip down memory lane. So if you take anything from this talk, and actually let me really quick do this for those in the room. All right, if you take anything from this talk, let's go back one. The key takeaways are that Since the launch of GPM and even before, slightly before, satellite, airborne, and ground-based observations have significantly enhanced our understanding of snowfall properties and processes. As well, these ground validation efforts and activities have supported and inspired multiple generations of scientists. We've seen that theme throughout all these talks, actually. I'm sorry, I'm not showing all the campaigns. I wanted to focus on the GPM, GV campaigns that have focus on snow. So what you see here is LPVEX in 2010, GCPEX 2012, Olympics in 2015, Ice Pop in 2018, and of course, Impacts, which was recently wrapped up. And I want to talk about some key instruments that might not be the instruments that people think of, the flashier ones. It's more these ones we can get our hands on that are very robust and give us a lot of information. And starting with the pluvio gauges, so these simple bucket weighing gauges, but they give us high temporal resolution rainfall and snowfall rates. We also have a lot of networks of parsivals, so these laser distrometers that give us information about particle microphysics and hydrometeor type. We've deployed tons of MRR2 and MRR Pros, which are these very robust profiling radars. So you have a profile of reflectivity and other variables right above you. And side note, they can also withstand being cords being run over by a snowblower. And then the PIP, the precipitation imaging package, which is a video distrometer with particle microphysics, precipitation rates, and snow density. I want to take just a second to talk about the PIP a little more because it was fully developed under the support of the GPM GV program developed by engineer Larry Bliven with the support of Walt Pettersen and Dave Wolf. It's been deployed all over the world and it captures these lovely videos. You can see these shadows of snowflakes and has been used in tons of different interesting studies. All right, so let's go way back to 2010 to the light precipitation validation experiment in Finland. So this is the Gulf of Finland. This is all the activities during this experiment. So there was tons of those parsivals, those laser distrometer instruments deployed. There was a bunch of gauges and distrometers put out, as well as plenty of MRRs. This one happens to be on a ship. And all this together gave us a lot of information during that winter 2010. Another winter experiment was the cold precipitation experiment in Canada. You see here in Ontario, you can see Toronto there and the Great Lakes. And again, we had lots of different radars, some of the flashier ones, but the trusty MRRs were out there giving us information, as well as this beautiful field of snowfall with distrometers and gauges giving us more snowfall information. And of course, the PIP, the precursor, the SVI, as it was being developed. I'm not going to go through all these, but I just want to say these instruments have been everywhere. They've been in the Olympic Mountains. You can see gauges and distrometers on this University of Washington trailer, as well as the PIP there, buried in snow, but don't worry, it got dug out. Spoiler alert. And Ice Pop, of course, another PIP in the snow, withstanding a lot of heavy snowfall and impacts, has, I don't know what I cut off, but that's the GALE. That's the GPM Atmospheric Instrument Laboratory. So this was recently developed by the folks at Wallops under the support of Dave Wolf and has been going out helping support impacts. So all of these limited field campaigns have given us a glimpse into a lot of information about snowfall, but we also have GPM supporting these long-term sites in Marquette, Michigan since 2014, in Huhtila Station, Finland since 2014, and Wallops Island for more than 20 years has had a developing precipitation instrument site. And what this has led to is some really interesting science that has been done with this. I can't cover everybody's, but there's so many good papers out there. Even with these relatively simple but robust instruments, we've been able to create an extensive data set of snowfall observations at diverse locations globally. You can see here on the right for over 10 years. And we have over 1 million precipitating minutes of data. So feel free to contact me and people at NASA to get into that data. Also, this has led to us, these snow microphysical observations, for example, particle size distribution and density distribution, have led to better snow mass retrievals. For example, we can get snow rates, we can get snow liquid ratio, and mass dimensional relationships, for example, from our Finnish colleagues here. And by using modeled particles, plus all of this measured information from GPM GV microphysics, we've been able to develop databases of key snow properties, which in turn have led to improved retrievals for GPM. Specifically, this is an example of a neural network retrieval developed by Randy Chase and Steve Nesbitt. And you can see down here that we're seeing very good ground truth comparison. But the most important thing about these ground validation campaigns have been the people. Going back again to LPVEX, We see a lot of photos of people doing activities. Nothing makes you bonded to your community like putting instruments out in the cold and snow. You see Patrick Gatlin here safely working on a tower. Dimitri and Tristan are checking out this instrument. Walt Pettersen leading a discussion of LPVEX. You can see a lot of GPM people in the crowd there. And Tristan Lecquier, maybe he was inspecting the aircraft. I don't know what's going on there. But yeah, same thing with GCPEX. We have Walt and Gail standing proudly in front of the 2D VD instrument. Gail and this was like central command for which is very Canadian looking on the inside as well with all that wood paneling. Mark Cooley excitedly looking at some data with Dave Hudak, and Steve Nesbitt as an early career professor giving an interview about to the Weather Service. And finally, this has been a theme throughout all these talks, but oh, sorry, skip one. The Olympics folks, I don't want to leave people out. Like I said, the PIP got dug out of the snow. We had a great collaboration with the Korean Met Agency and Ice Pop, and of course, more activities during impacts. And like what was alluded to before, there's been a through line of people sticking with the GPM program, being inspired by the science and sticking with it. Steve Nesbitt did his PhD with TRIM and early career science here during GCPEX. Myself, it's me, I'm behind that. I'm fixing the radar, we're looking, Mark's giving me the calibration, so that's in 2014 as a grad student, early career researcher. And Steve has continued to do this. This is part of our project in 2023, deploying the University of Illinois SCAMP with a bunch of his grad student group, which has been great. And at the exact same time, I was in Marquette with a great group of folks, grad students, as well as Norm Wood, who's been part of his GPM forever as well. And so I just wanted to make the point that nothing bonds you like those GV efforts. And a lot of us continue to do those in the future. So thank you.
Dalia probably needs no introduction, but I'm going to give her one anyway. So this, we're shifting gears to applications now. She's currently the director of Earth Sciences Division 610 here at Goddard. And prior to that, she was the chief of Hydrological Sciences Laboratory. A really long time ago, I think she was an intern with Bob Adler's group a long time ago. And she stuck it out anyway. She's still here. She was the deputy project scientist for applications before she moved up to a management position and had to relinquish that, at which point Andrea Portier took over as the senior lead for applications. Dalia has worked with the broader NASA's community, of course, in disaster response, doing flood work, landslide work. You could ask her later about getting landslide reports in French. So, Dalia.
All right. Well, it absolutely warms my heart to see so many friendly faces. So as I've been with TRIM and GPM from the beginning of my professional career, and it really is wonderful to stop and celebrate the accomplishments of what we've done. And so in that vein, Andrea has asked me to talk about our applications activities and some of our outreach. But this is the work of Andrea, this is the work of Dorian, of previous people in this position, Kristen Weaver, Jacob Reed, Ryan Fitzgibbons, the SVS, production, live shots, and you all who have contributed to so much of what we've done to support how people use the data. Oh, we don't have to keep looking at me, sorry. All right, so we have been able to be incredibly successful in how we harness and apply GPM data all over the world, right? And we're building on this tremendous legacy from TRIM and the users that have been really at the heart of what we do from the very beginning when TRIM First Light was in the late 90s. So we've been able to kind of look at this, the scope of what GPM has been able to accomplish in applications. And we were actually able to do this because pre-launch, Arthur Howe and I were talking, and he said, why don't you come work on this on GPM? And I said, okay, that sounds great. And with a very reasonable budget and blank canvas, we got to craft the entire thing. So I think, we hired Dorian, we hired Jacob. I don't think we can really do that anymore. And it's given us this amazing autonomy to build a tremendous capability across the board that I think NASA has looked at to apply in the future for mission applications activities. So it was in a unique time and place to be able to do that, but wow, it's been a great journey. So just want to, there may be a little bit of click fatigue, so just bear with me, but these are just some of the activities that over the last 10 years we've been able to achieve pre and post launch, and how we've been able to reach the community through trainings, through workshops, engagements. And many of you are featured in these applications highlights. We have over 180 of them. The GPM website is very well trafficked. So we're going to go through a lot of examples here, and Andrea had fun with the animation. So if you get dizzy, just close your eyes. All right, so agriculture, you'll hear afterwards from my colleague Faisal Hossain. We'll give a little bit more about what he's been doing and working on the ground. So GPM has touched pretty much every sector of our economy, from agriculture, water security and food, looking at, with tribal nations like Navajo, looking at water budgets. We're looking at disease and understanding how GPM can inform malaria outbreaks, cholera outbreaks, and the like, as well as, of course, contributing and advancing our operational capabilities through new research and understanding weather forecasting, and how we work very collaboratively with our partners at NOAA to transition much of that research. My area has always been in landslide risks, so well, I wasn't, but our team was in Rohingya camps and Bangladesh, and showing how GPM data can be relevant to understand kind of the location and impacts of migrating populations. And then, of course, across the board, looking at disaster response. I was actually just visiting our colleagues at the Pacific Disaster Center, and they've been able to incorporate many of the products, but GPM kind of is still paramount in what they bring in to provide disaster support from around the world. On the defense space, right, so we've worked to develop modeling capabilities that are assimilated into our DoD colleagues' operations, including the Air Force. GPM helps fill gaps in the 557th Weather Wing and others. And we help to not only understand kind of where we have precipitation, but how that impacts food, connectivity, and supply chains. And so working across those domains as well. NASA tracks elephant migrations. Didn't know you knew that, but apparently there's a lot of activities happening to understand where migrations may happen that impacts farmers. And then we had this really interesting engagement on energy and understanding where wind power and precipitation together can corrode wind turbines. And so a lot of this came because of a lot of the stakeholder applications workshops that we've had over the years. And so we can have the people from those industries come and speak about what we do. So microinsurance, so Micro is a good example of how they provide automatic payouts to farmers and small business owners in Central America based on GPM data. So the accuracy of iMerge and the continuity of how we can understand that into the future is really critical for a lot of business operations. All right. We also talked to a lot of people, including celebrities. This was really fun. So this is Joseph Gordon-Levitt, and this is during COVID. So it was like an 11 p.m. interview from my bedroom in COVID. We did a lot of those. We also developed packages to really demonstrate not only what we do, but who is behind it, so that people understand career tracks to inspire those that move forward. Again, you'll see out in the lobby, we love Lego. It's changed names over the years, but it's rooted in a tremendous following. So 1 million educational views. And Dorian Janney is a veteran educator and has really guided the development of capabilities so that teachers can use this in their classroom. And back in, I don't even remember, 2015, we actually compared lessons being taught in classrooms with GPM data versus the normal class, and the retention of students was incredible. So it was scientifically validated that it helps to really engage students. And then we engage in podcasts and live shots and all of the things that we do to really increase the visibility of where we are. Dorian has been leading, and right now there's a commodity classic where we have a NASA delegation to Houston to talk with the major ag companies around the US, and Water for Wheaties is a great way to connect people's everyday life and to really where it comes back to why satellite data is so important. So I really encourage you to take a look if you're excited. If you need some materials, let me go back. If you need some materials, Dorian and Andrea and others are here to talk. So thank you so much for inviting me to speak, even though this is all Andrea and Dorian's work. And it's so nice to see all of you.
This is the 10th anniversary. I can embarrass Dorian, or Dalia just a little bit. She was one of the anchors for NASA TV for the launch of GPM. And you were on camera for 3 hours and you were great. You know, it's like, wow. So one of the things that I've learned over the last 30 years, now 30 years ago when Bob and I started out in this business of handing out data, we would create data sets and we'd flop them out onto the internet, open science, by the way, 30 years ago, and expect people to come use them for applications or science or whatever. And what we've learned over the last 30 years is there's a valley of death between the data sets that we produce and the actual applications that we end up impacting people's lives. Dalia has been instrumental in that, in the landslide and flood end of things. And our next speaker, Faisal Hossain, is just the poster child for making this happen. He is the John Kiley Endowed Professor at University of Washington in Civil and Environmental Engineering. He started out in hydrology, but he's gone into sustainable water resources, engineering education. He doesn't mention here that he was once a summer student with me. And I followed his career ever since. His mission is to make access to information on water a fundamental right to all nations and all humans. And he's done this in the most practical way that you can imagine, which is probably what he's going to talk about.
So thank you again. Thanks for inviting me. And thank you, George, Andrea, and everybody else, the organizers. Very honored to be given a chance to talk about certain perspectives we have from a more, the global use of GPM. I know time is tight, so I'll get straight to it. And what I thought would be nice is first, we're talking about 10 years of GPM, but what if we go a little bit further, 20 years back, I was reminiscing about this, right at that time, straight out of grad school, many of us were thinking about, okay, we have all these spaceborne capabilities. Can we have a completely spaceborne system to track certain phenomena of interest based on which we make decisions, for example, floods in this case? And the question was, can the cost effectiveness outweigh prediction uncertainty? But back in 2004, I think even when you tried to implement that, you realized that we didn't have all the other infrastructure or the tools in place. For example, we really didn't have sub-hourly high resolution precip data. Back then, at least in water resources, water management, the open source, open science movement wasn't as thriving and vibrant as it is now. There wasn't really cloud-based distributed computing at our fingertips. The accessibility data wasn't as equitable as it is now. And some of you might recall this because I started my grad school with these exabyte tapes, which limited your mobility. You had to put it in your servers and be close to that place and do all your computing and analysis. Now, 20 years later, we've got GPM. Great, fantastic. We have open source, open science movement with FAIR principles that is robust and vibrant, at least in water resources, earth science, hydrologic sciences. Yes, we've got lots of cloud computing, distributed computing options. Many of them are freely available, quote unquote, free, Google Earth Engine, AWS, all that. And I believe we have much more equitable access to big data than what we had, say, 10 years ago. So what this means is that, if we combine all these with the GPM data, the precipitation data, we should be able to, and we are now able to create user-ready, not just user-inspired, but user-ready, user-owned GPM data-driven tools that can potentially improve livelihoods and owned by the end users. So what I'll do here is I'll try to quickly go take you on a world tour. I'll start in South Asia, show some success stories there. Dalia referred to it a little bit, then go to Southeast Asia, and go to Middle East, North Africa, then come back to my neck of the woods, Pacific Northwest, and then I'll try to end with a global effort that we're doing, and end with some last words. Basically in South Asia, this is the one major success story we've been able to have is, using GPM data to get more drop per crop. In other words, basically informing farmers as to when to irrigate, how much to irrigate, because as part of that equation, when you're trying to figure out, you need to know how much it has rained in the past. So the whole idea was to create a more decarbonized, climate resilient food production system. And we launched it in 2016 in Pakistan, and then it scaled further east in Bangladesh. And it's been owned by the end user agencies. And recently there's been a story about this where the government of Bangladesh implemented it operationally into their own decision-making system. And the impact evaluations we've done came out to be quite interesting, because in that region, farmers generally tend to overwater, over-irrigate. And having that key piece of information from GPM data can really be very helpful. So here are some stories, publicities by NASA and other forums done. So next is Southeast Asia. So you see the Mekong countries here, the dams. This is courtesy of the NASA Survey Program and USAID. So the Mekong region is, of course, it's made up of China, Laos, PDR, Thailand, Vietnam, Cambodia, and it's heavily regulated, lots of dams. And one of the key interests in as far as understanding water availability goes is to know what the dams are doing to downstream regions. So we had built for the Mekong River Commission, that's in charge of coordinating among countries, a reservoir assessment tool that does a mass balance kind of sort. And one of the key inputs to this is actually inflow, which is again derived from GPM precipitation data that forces a hydrologic model here. And about 2 years ago, this was actually adopted on an experimental basis by the Mekong River Commission. So if you go to their website, you will see a little link and you can check that tool is running, and it's operationally ingesting iMerge late run data. So here's some stories that we had. Let me see if I can play a video here. Well, that's what we can skip. Here you go. So this is on the Tumley app. I think it's not playing, so we'll just skip. So now next we go to Middle East and North Africa. So this is more nascent than the other applications. So there are two major river basins, as you know, the Nile and the Tigris-Euphrates. In both cases, the situation is somewhat similar. It's heavily regulated. The availability of water is quite asymmetric, and upstream, there's more regulation than downstream. And there's a genuine interest on knowing what the reservoirs are doing. So again, in this case, we have GPM precipitation data being ingested operationally to understand the inflow to the reservoirs, the dynamics, and how much water is really available on the surface. So we have these two tools, and we essentially have created enough tutorials so that the stakeholder agencies can benefit from these predictions. And again, some feature articles that we have here. Now, closer to my neck of the woods, this is very near and dear to my heart because in the Pacific Northwest, but it also addresses tribal fishing rights. I know 2024 is the 10th anniversary of GPM, but it's also the 50th anniversary of the Bolt decision. For those of you who don't know what the Bolt decision is, it's a decision made by Judge Bolt, a federal judge, where basically the state of Washington and all the dam agencies were required to do the needful to ensure tribal fishing rights so that fishing could happen the way it used to happen before dams came about in the Columbia River Basin that you see here. So on average, about $300 million a year is spent on fish mitigation, and river temperature is critical here. And as you know, if you want to get a more holistic view of temperature from space, you would want to use Landsat data perhaps, because you've got multi-decadal data set. But as we are trying to engage with the government of sovereign nations, we realized that, because the temperature is heavily influenced by the dam operations, we saw that the moment you include reservoir dynamic information in your prediction of river temperature, your performance improves. And that reservoir dynamics is coming from actually GPM emerge data, again, forcing a hydrologic model to drive the reservoir dynamics. So there you see the connection, from GPM to reservoirs to tribal fishing rights and, indigenous rights for fishing. And we created this tool, we called it Thor, Thermal History of Regulated Rivers. So my last point here is more global, which is, there are many global phenomena that we could address or we can talk about, but one that we have been trying to address is reservoirs. Here you see in the global south, there are lots and lots of reservoirs where generally you don't have a lot of in situ data or ground infrastructure for measurement of whatever geophysical variables that you need to keep track of. And there are new reservoirs also coming up, not in the global north or the developed regions, but mostly in the developing regions. And one of the issues here is that we need to be able to monitor these reservoirs effectively. So earlier I mentioned about this reservoir assessment tool. It's gone through many version changes, but we realized that really to empower communities and to help them really build by themselves the tools they need to track reservoirs, we have to really do a lot of work in the software and architecture. So the version 3 came about, and in this version 3 of the reservoir assessment tool, if you want to run cron jobs to do operational monitoring reservoir in your region of interest, it needs precipitation data. And we have used the iMerge later on as the default option where it automatically downloads the data and then runs all it's needful to start doing its job. This tool has had 1,500 downloads since last year, and it's currently operational in a couple of river basins for many other many water management agencies. So this brings me to the end of my talk, and my last words basically is, for a lot of decision making and impact and making sure that these tools are user ready and owned by the user community, we really need operational continuity of GPM precipitation data at low latency. It's really a must. I just shared with you a snapshot of what's going on. That is a little bit biased from my perspective because I've been involved with it, but there are lots and lots of amazing success stories, as Dalia have mentioned before me and other places. So with that, I'll end, and I do want to thank, of course, the broader GPM community. As George mentioned, it takes a village to come to where we are now. So thank you, everyone, for this gifting the world this amazing mission that is doing so much good for the world. And that's it.
So this brings us to the end of the formal part of the program. I get some last words. You perhaps learned a few things today, had some good memories. So we've had a chance to celebrate successes, and now is it's up to those of us who are current to build on these successes and keep moving this forward. To a certain extent, the question is, what have we done for everyone lately? And it's up to us to do the new science, to do the new applications, and really make this move forward. I would like to thank Andrea Portier, who's going to be embarrassed. She is the driving force behind the organization for this, and if it were not for her emails that she felt bad about sending me, we'd still be figuring out what date we should do this. As well, Dorian and Jenny has helped out. And Lisa Novorchek has done the administrative stuff, and she's, I think, around the corner. So I thank her as well.